Can you see the screen?
Yes.
You can see the screen.
Yes.
Hello?
Can you hear us?
I can hear you.
So we can see the screen. It's okay. You can start. Please.
Okay. Good afternoon, colleagues. It's my pleasure to participate in this joint workshop. I'll give a general presentation on on what we do here at the CSIR in South Africa, particularly on high value equipment. So moving on, the outline briefly is as follows: overview of the CSIR laser-based manufacturing, some few case studies of things that we've done in the past. Where do we stand as far as additive manufacturing is concerned as of to date? What in general the South African context is additive manufacturing implemented, and some remarks on other institutions, their efforts on 3D printing. Out of the colleagues sitting in the meeting here, it's only Professor Vladimir that has been to South Africa. We have not had the pleasure of welcoming Maxime for now. So the National Laser Center is just a sub-unit of the CSIR. It's actually quite a small unit with a total staff of about 65. 60 of those are in science, engineering, and technology. The complement of the staff, most of them just under 17 in numbers, hold doctoral degrees. So per year, roughly we publish about 28 papers or thereabout. Just another point, as of last year, the NLC turned 21 years. So it's actually been in existence for a little bit of time. We try and do some kind of, take some patents and all of that regarding the work that we do. In terms of the total turnover in money, it's not really that big, roughly about 100 million or so. Did I skip some? Yes. Overall, the key objectives of the NLC. Firstly, CSIR National Laser Center provides a critical core of laser technology and expertise, simply because we specialize in laser technology. The areas that we focus on, we design, implement certain laser systems. These mostly around about 2 micron lasers, mainly for defense applications. So we develop laser-based manufacturing processes in metal additive manufacturing. We do some research and development on laser surface engineering. That includes laser cladding, laser joining. We do this in collaboration with some local industries where opportunities exist. We have a small prototyping facility where we can assist industry to make certain small products, though it's a relatively new endeavor. So some people might have an idea, but don't know how to start. We've got a little group that can assist them in that regard. Again, reinforced here, the key research areas, this prototyping facility. We have the so-called novel lasers, which are the 2 micron lasers I was talking about. Our group here is called Laser Enabled Manufacturing, doing additive manufacturing as well as surface engineering. We've got a unit that then whatever solutions we develop under item number 3 on this view graph, they can then take that and industrialize it. If there is no more research required, it becomes a routine. So we've got a group that does those kind of things. We have another group, biophotonics, is mainly focused on medical applications via sort of the main focus in any case sort of skin cancer. That's the main focus of that. At the bottom there, we have got what they call national programs. So the national programs, we assist the universities and whoever else, because we have, in some cases, we've got enough lasers that we don't even utilize. So we loan these things out to these universities to do their work. Hence we call it national programs. Going back in a slightly more compact view graph pictorial, which again illustrates our capabilities. We've got a small, hey, that's great. We've got a new effort in laser shock pinning. This has been going on now for about 10 years. Of course, the big area of focus in our site is additive manufacturing. Laser welding, we just do it not so much as a research focus, equally laser engraving and laser hardening, laser cladding. In some cases, we still do some research. In some cases, we actually do it as a service to industry, as well as laser cutting. And then why do we need, in our case, in the context of South Africa, in any case, these processes I was just describing, as a sort of third world country or a developing country, there are components that were bought years ago in terms of financial capability of replacing them with new components which we'll have to import. Requires that we look at different approaches. These would include, where possible, repairing those components. We've got a number of such situations here. As an example, the power, electricity generation units, some or most actually come up to the end of their life, and to build the new ones, obviously, it's extremely expensive. So we try and get them going for as long as we can. Hence, the requirement to refurbish instead of replace, because we don't, as a country, we don't have enough money to do some of those things. What are available technologies at our disposal? At least we have electric arc welding suits, laser cladding, thermal spraying. Now it becomes a question of which one will be suitable for a particular job. As a laser center, we obviously have more bias on laser-based solutions via laser cladding, which comes under many different terms and terminologies. So typically, of course, you know what is laser cladding. Simply melting of powder on the surface, get good bonding, characterize what is happening. We'll come back to some of these points, or at least in the case studies where we've applied this technology. As far as equipment is concerned, we have a number of lasers around here. We have nearly 10 fiber lasers across the department. We used to have this NDX laser from Roughness, which we discontinued. We don't use any traditional solid state lasers. So now we've moved to fiber lasers. However, we still do have a gas laser, the CO2 laser, 5 kilowatt. Now, where we've used the ESCOM is energy generating company, state-owned company here in South Africa, I was mentioning. So we use repair or laser cladding or additive manufacturing, for example, to repair these turbine blades, leading edges. You can see one of the blades, the corrosion on the blade edge. So we skim those things up and repair them. The other picture there shows number of these blades that suffer such fate, which we have to sort of assist and repair them for this particular company, ESCOM. We've got there also the tenons, which we build back so the blades can be put back on a machine. This is another power station also under ESCOM, where we've got these big blades that need repairing on the sides there. There's a power station at the back. So we actually apply a lot of laser-based technologies to assist the local companies. Yet another example where a journal is being refurbished or put back to life. You may say that that's why we are quite interested in understanding more on laser cladding, because we do quite a lot of it for big industries. Here's another case study. You can see there the problem of the tape casing in that nozzle. We had to sort of clad all of this thing. There's a big component itself, so there's quite a lot of activity on excuse me, laser repair of rather large components that we're talking about. So for extremely large components, this, by the way, it's at the factory where this component is being repaired. To assist in that, we've got what we call a mobile system. We just package the laser, put it on the truck, take it to where it's required. It may even spend a week or so in the factory doing some of these repairs. Here I show similar. where we've done a lot of work, which saved this company, ESCOM, a lot of money. This is the situation here is that ESCOM has got a large fleet of coal-powered stations. You may have read in the newspapers that we have a lot of load shedding because of the inability to buy new power stations. So we spend a lot of our time assisting them repairing whatever is there. In here, I'm showing you an example of, incidentally, in South Africa, there's only one nuclear power station, which was built by the Germans. Occasionally, this thing suffers from stress corrosion cracking. So we had to develop some solutions to repair this thing without turning off the power station. There are my colleagues here busy doing exactly that. Now moving on the laser shock pinning, I'm sure you're all aware of laser shock pinning, or if not, an equivalent of it will be the usual hammer pinning or type thing to induce compressive stresses on components. So we started a program, I said nearly 10 years now, which is a sort of description of what happens in the process of inducing compressive or relieving tensile stresses. So applied this thing again on some of those turbines. And the advantage of this process, you get quite deep depth as opposed to shallow relief depth with the mechanical system. And also the surface finish is rather quite good compared to the usual traditional shock pinning. Now, some projects around laser welding, particularly dissimilar metals. So we've got some projects going around, taking place in laser welding. These are sort of the type of metals that we've looked at: titanium to stainless steels, aluminum to coppers, aluminum to stainless steels, with some quite good results. And we've applied these to some components that certain companies tend to be interested in. Do you still, can you still hear me, Maxim?
Yes, everything is okay.
Okay. Now, I'm sure Washington has got a picture of one of the rather large 3D printing machine that we've developed here. So we noticed that we're pursuing 3D printing as well as 2D. So we've got some capability in 3D printing. I'm sure all of us know what the 3D printing is. We have two systems, powder bed system as well as the powder blown system, or what they call these days direct energy deposition. We, as far as that is concerned, we've got commercial machine from Optomic. We also have, we use robots, Kuka robots and all of that to build certain parts. As far as powder bed is concerned, we built this machine here, Aeroswift, which I think Washington will mention in his presentation. Obviously, there are pros and cons of the two systems. As SLM is more flexible, we can build more complex parts and surface finishes quite good. With the system that we have here, we don't have this limitation of part dimension. Our system is designed to be 1 meter by 1 meter by 0.6. So it's quite a rather large system. Of course, the disadvantages with LMD in terms of complexity. The machine that we have cannot handle extremely complex parts. So you cannot make, for example, parts with a roof. It's not flexible enough for those type of applications. This is a picture of the optomech machine that we have. And it's got relatively good work envelope, 1 meter by 1 meter by 1.5. So it's okay for a number of our applications. And okay, we've mentioned the limitations on these things. These are some of the parts that we built out of that LMD system, the optomech system. I have to say that as far as a lot of customer take-up, we haven't actually built a big customer base, but just we're trying to get there. Now, the other big machine, Aeroswift. The idea is to build very large components for aerospace industry. It's not limited. We limited it to titanium so far because of the system is quite large and cross-contamination could potentially be a problem. This is this actually still a schematic of the machine, but this is how the machine looks like. We have the 5 kilowatt laser. The envelope of it is that much, and it's scalable. It can scan extremely high speeds, 50 meters per second. We don't use multiple beams on this thing, just the scanning. It's got preheating capacity of up to 600 degrees. Naturally, we use inert gas in it. Okay, this was just the development phase of the machine. So you try to put some systems to alert us whenever there's an error during the build, and possibly to alert too early for a system that size and discover an error after a number of hours later. Then that's very, very costly. We've got these cameras that put in there for surveillance of the parts and see if there are any errors happening. Let me show you the type of parts that we built. That this is a drone that was just to test the system. You can see this way 80 components that we kind of testing, still optimizing the machine, trying to demonstrate that first they can build, second they can build complex parts. So this way, any attempts, you can see their supports and surface finish is quite good. A lot of rather complex geometries in the build process. Some more examples of what we built. This is one of the largest, actually not the largest, but quite large part that came out of that machine. The machine is totally home built. It was built here at the CSIR. So we're trying to demonstrate the capabilities of first to build the system, and secondly to make sure that it does complex parts. Overall, in the country, there are lots of other efforts running to try and strengthen or at least increase the South African foothold or visibility in the additive manufacturing space. Luckily for us, our government is quite supportive and has put in a lot of money actually to assist in this effort. The machine that we showed you there, most of that money came from the government. So in that sense, we're fortunate to have those. I'm just trying to show you here of various universities that participate in additive manufacturing. Nearly almost all the universities in the country participate. We focus ourselves, we focus on metals. Other partners do polymers and so forth. But our main focus here is metal additive manufacturing. We also have a program that supports those universities via the government again. So we get financial assistance that comes to the CSIR. CSIR distributes it according to its strategic requirements, because we cannot do everything else here. We need some assistance from other partners outside the CSIR. So we sometimes kind of, because of the difficulty of the large system, we've built a smaller system with exactly the same process parameters, except for the size in this case. This we hope will assist us. When you want to build something, you start on the small system, make sure that all your parameters are right, and then you go to the bigger system. In pictures, this is how it looks like. Here it was still being built, but it's almost nearly finished now. It's on the testing stages. We've done some components out of that. So the colleagues still looking at improvements on that particular machine. I think I will end my presentation there. These are some of the partners that are involved, at least in additive manufacturing. Thank you for your attention.
So, thank you, Prof. Pityana. We have some time for questions.
Yes.
Are there any questions?
Okay, why not?
Yes.
I have some question. Okay, Sisam, when I visited your country, I asked and you presented me some presentation about development of this kind of technology in South Africa, but you exclude several slides concerning some special applications, special areas of applications. And my question is some common words. Does that direction develop the same successful as others presented now? or maybe you have some problem in that direction. Do you understand me?
I'm trying to understand.
Do you remember what kind of slide was excluded from my from the presentation which were presented to me?
Oh, the time I wasn't. The time I was in Russia.
Mhm. I mean, okay, I explained to Maxim, for example. Now, CSIR presented us application of this technology in civil application,
Yes.
And I ask you some common words about other one.
Maybe the other ones are confidential.
But
You know,
common words, it is successful in that area, or maybe you have some serious problems there.
No, we don't have any problems. Remember the strategy keeps changing.
Mhm.
Our focus keeps changing. In order for you to remain relevant, you have to kind of go with what is of interest at that point in time. So, for example, the current interest, although I'm sure all of us might agree that what COVID has shown, I mean, we all believe that aerospace is the most important industry. With the COVID and people not flying and people canceling orders of airplanes, we don't know whether it will go back to the same situation as it was, or in fact, it was 2 years ago, aerospace industry was, at least additive manufacturing in aerospace was a big thing. I cannot say the same. I'm not sure going forward whether we'll maintain that position. So what I'm trying to say is we had a lot of emphasis on aerospace application in the last 5 years. Going forward, we might have to change our approach because the aerospace industry might be declining. So hence we continuously adjust our objectives. Doesn't mean to say that we're experiencing problems, but the situation requires different approaches. Isn't it, Brother?
Okay. Nevertheless, you printed many papers about the titanium, aluminum alloys.
All right. Now I was confused, slightly confused about to what extent do we want things outside the main program. That's why I did not put those. No, it's not that we can make another workshop and I can present those. I have, yes, why not? I can share those maybe in in another workshop.
Okay.
At least Professor Niziv can make a vacation to South Africa, and he will listen again to the progress in other applications. Yeah, we understand that aerospace can decrease, but at least you have your energy application. So I think additive manufacturing won't decrease much, disregard anything. Okay.
Okay.
Does anybody have questions?
Can I have one?
Sure. Alexander Dubrov.
Yeah, thank you, Professor, for your excellent presentation. Can you go back to the slide number 20?
Okay.
You said there was some like nuclear station, and you did some works using additive manufacturing technology to repair, as I understand, or some works there.
Mm-hmm.
So the question is, did you get in some issues with the certification, or because nuclear stations, I believe it's an area which is have a kind of regulation, maybe government regulation or
safety critical, as it's written.
We actually, to be honest, we had to do a number of off-site and monitoring of the nuclear regulation people. So it wasn't just go in there and do this thing. You are correct, it is highly regulated. We had to develop the process off-site, get the nuclear regulatory body to satisfy themselves that it was a long process.
Mm-hmm. But you succeed.
Yes, we succeeded.
Okay, very good.
But it was a long process.
Yeah. Okay.
Yeah.
Thank you.
Thank you.
So it took much time, but I think we can, if somebody has any questions, we can have a short question.
Okay.
Okay, let me ask a short question. So are you involved in developing some technology standards in additive manufacturing?
Say that, Maxine, again.
Are you involved in developing technology standards?
Oh,
for additive manufacturing and LMD especially?
yeah. So we have some representatives that are involved in the development of standards. The numbers of these standards just slip my mind now, but there are some colleagues who are involved in that. Not myself personally, but representing our group in the development of those standards.
Mm-hmm.
Yeah.
Okay.
So, for example, some of these things just to give you, we received a request from Boeing. You know, they have their own ways of standards of making certain components, that we reproduce those components using this high-speed machine, and so they can test. This is one example where sort of the match between the actual players and what we're developing to make sure that it actually is in sync with what is required. So we do adhere to those standards.
Okay. Okay. Thank you.
Okay.
So let us continue our workshop. I was planning to make my presentation next, but if asked me to put him after you, Prof.
Okay.
I don't mind. That's why he will start his presentation now.
Yeah, I think he wants to leave quite earlier.
Okay.
Mm.
If can you hear us? You can start. iffy, I'm sorry. We can see you, but we can't hear you. Could you please tell something?
If
No, we can't hear you.
let me try and call him.
Can you hear me?
Yes, now we can hear you.
Okay.
But your voice is rather low. If you can be
I'll try to speak louder.
okay. The voice is very low. You can start your demonstration.
How do I share?
In front of you, you've got a green button to share your screen.
Entire screen, window, and then Microsoft Edge tab. Which one?
Okay.
I've never used Zoom, sorry.
Go into on your work panel. It will come. It will show the green share screen.
Oh, yes.
Mm.
Would you start?
I see the reporter and his presentation now. What's the problem?
I don't know.
It's not
Iffy,
landing.
are there any problems? We can't hear you again. I guess your microphone is turned off. We can't hear you.
If you are mute,
Yes, you need to unmute yourself. I will try to do it for him. No, I can't do anything for him.
But he doesn't speak.
No, he's muted.
like saying, is Washington still here?
I guess yes, he is here.
If if you want to allow Washington, I can go to his office to go and help him quickly.
Okay, okay.
All right. Maybe allow Washington to present.
Okay, we can start with Washington.
Okay. Are you ready, Wash?
Yes.
Yeah, I want to just go and sort out Iffy.
Okay, not a problem.
Okay.
All right. Just a second. I'm trying to share my screen now. Please let me know when you see my screen.
Yes, we can see it. And we can hear you very well.
Okay, wonderful.
Please start.
I'm gonna go to the presentation mode. Okay, good day, ladies and gentlemen. My name is Washington. I am currently working at the CSIR. I've been in the organization for almost 5 to 6 years now. I came in as a student doing my master's. And actually, that was the first time I started learning about additive manufacturing. I come mostly from a material science and metallurgical background. I was introduced to additive manufacturing through my master's studies. And then since then, I've been really working around additive manufacturing and different phenomena in additive manufacturing. So today, I want to present some of the work that we've been doing in the group. And this is actually related to my PhD studies. I'm currently doing my PhD studies almost in my third year now. And I'm also working full-time for the CSIR as a junior researcher. And yeah, so I'll be sharing with you some of the work that I presented this late last year at some local conference with you guys. So we were looking at the residual stresses, porosity, and surface roughness, particularly for the titanium 64, which was manufactured using a high power laser system. Prof has already alluded to the systems that we have in our research group. I will just touch base on that as well. The outline of my presentation, so we'll just briefly look at the background and the motivation of the study, the aim and the objectives, briefly go through the methodology that we used in our investigation, some results that we were able to obtain, and then of course, some conclusions at the end. So many of us here are familiar with additive manufacturing, especially laser-based powder bed fusion. Some call it selective laser melting. Some prefer to call it direct metal laser sintering. But I think quite recently, LPPF has been sort of a common term that has been recognized to classify metal-based additive manufacturing. Quite a powerful technique, really, if you look at its capabilities, very capable of producing complex parts that were rather impossible to manufacture in the past using your traditional methods, such as your castings, your forging, or even such as your casting and forging, yeah. And with the advent of additive manufacturing, we've really seen that it actually stretches the boundaries. You are able to produce parts that any design that you can literally think of, and then just feed it into the machine. And then the rest actually is done by the machine, the powder and the laser does everything for you. And we have seen with research, ongoing research, that the technology is quite capable of producing parts with somewhat acceptable mechanical properties. Okay, well, there's some controversies there, but yeah, we have seen it's capable of producing parts with acceptable mechanical properties, sometimes superior due to the fine microstructure that's formed during the manufacturing process, since you are using a very small molten pool, and then this promotes a very fine microstructure. It's very attractive to the aerospace and medical industry for obvious reasons, due to its capability to produce complex components which are usually required in these industries. Of course, lightweight also being one of the requirements in the aerospace and medical industries. However, there are still some issues with additive manufacturing. And here I just mentioned a few of them, the obvious ones, that really inhibit the widespread adoption of this technology. Some of this talks to the building rate, actually. The process itself, the actual building of the component can take long, a matter of 2 to even 3 to 4 days, depending on the size and complexity of the part. Of course, you do gain some benefits in the pre-design that you don't have to worry about designing patterns and dies anymore, but the actual printing of the job can take long. And of course, the surface finish is also a factor, especially if you're looking at aerospace components where fatigue strength, it's really an important parameter. The surface quality there, the requirements usually is below 1 micron, which we are not able to get with additive manufacturing unless you apply some post-processing finishing on it. Of course, random porosity being another issue, and porosity can affect your mechanical properties. The higher residual stresses develop due to the rapid heating and cooling cycles. Of course, these residual stresses, when they're high enough, they can generate distortion in your part. This can lead to part inaccuracies. It can even lead to cracking or delamination of the parts during the build. And of course, anisotropy in mechanical properties in the S-build condition. We have seen that actually if you test the material in different directions, you tend to get different properties. But if you apply post-heat treatment on it, you can actually get rid of the anisotropy and recrystallize the microstructure. So I'm only going to be focusing on the first four, which really talks to the build rate, the surface finish, and the porosity that you're likely to get due to a variety of reasons other than processing parameters, and of course, the residual stresses that we're able to characterize in the samples. Here, I'm just showing some of the pictures of the components that a component that we attempted to build late last year. We were not successful in it. We had to stop halfway through the build because of delamination and cracking. So, of course, the first delamination, we didn't detect it. If you look at the bottom picture between the part and the supports, we could only detect that later when we removed the part. And then, of course, there's cracking that took place just along the rib of the part. It was cracking. And yeah, we had to stop the build because of other laser issues. We lost the intensity during the build, so we had to stop and investigate what was happening. Upon that, we discovered there was actually more than one problem. That's when we discovered that we also have issues with delamination, we have issues with cracking, which is really why it's of interest for us to investigate residual stresses, understand this phenomena, and see how we can mitigate it using our own system to sort of reduce these problems that we're currently encountering. So for some of you that are not so familiar with residual stresses, so by definition, residual stresses are the locked-in stresses that exist in the material and structure without an external load applied to it. So this remain even after processing, they are locked-in stresses. And then they develop as a result of non-plastic deformation during mechanical processing, or as a result of phase transformation, or as a result of thermal gradients during manufacturing. The stresses can be detrimental or they can be beneficial depending on their sign and location on the component. We know if you have compressive stresses, they are likely to improve your fatigue resistance. Without stresses, then this can actually have some negative effect on your mechanical properties. Just a schematic diagram trying to explain how the stresses develop in additive manufacturing. So basically what you have the laser that heats up the powder and your base plate. At that point, you start to have the temperature rising and then you get expansion. As the temperature rises beyond the melting point, you have some melting of the powder, you form the molten pool, but in the liquid state, there's no stresses. But around the heat affected zone, you start to get some tensile expansion there, but the material is not expanding as rapidly as it should because of the constraint around it, because of the cooler material around it is constraining it from expanding. And then when the laser is switched off, you get contraction. And again, because of the constraints in terms of thermal gradients, the cooler material constrain the hotter material from contracting at the faster rate, and eventually end up having some tensile stresses on the surface. Of course, there are methods that are currently being used to understand this phenomenon to try to find ways to manage it. There's an in situ stress relieving methods, which really relies on the optimization of processing parameters or application of preheating of the base plate to sort of minimize temperature gradients and residual stresses or distortion during the build. Some methods rely heavily on post-processing, where you apply heat treatment to get rid of the stresses before you actually remove the part from the base plate. You do some stress relieving and annealing it, then you know that all the stresses are alleviated, then you can remove your part. There's also modeling and simulation efforts where these things can be sort of predicted well in advance before even attempting to build a part, and identify some areas of concern, put some measures there if you have to put supports, or just apply some sort of control measures to manage those problematic areas. Again, in recent years, we have seen there's been a drive from manufacturers and researchers to really focus on expanding the capabilities of their machines by increasing the build rate. At the start of my presentation, I did mention that one of the concerns of additive manufacturing is the actual building process. It can take long, so now people are trying to push the build rate so that they can improve on the productivity of this process. And of course, the build volume has also been a limitation in some areas. So in terms of your part size, you were limited. As such, in terms of applications, you were constrained because of the build volume that comes with commercial systems. Here I'm showing a model from SLM solution, SLM 800, quite a big machine, quite a big build volume, 500 by 280 by 87. The system uses multiple laser systems, simultaneously scanning the powder bed. And then the principle is called parallelization, and the number of laser sources you can really increase your theoretical build rate almost linearly. But one obvious problem, especially for research institutions or countries that have limited financial resources, such kind of a machine obviously become expensive. Multiple laser systems will really dramatically increase the cost of this equipment, and for some of people, this might be an issue. So really, we're looking at other alternatives other than using this system. For us at the CSIR, quite some time we've been working towards building this large envelope, which is called the AeroSwift. It's a long project. It's been in existence for more than, well, from the initial design and testing phases for almost been running for almost over a decade now. And then the system is equipped with a 5 kilowatt laser system, fiber laser. The build envelope is 0.3 meter by 0.6 and 0.6 meter. We use argon as a shielding gas during the build. The preheating system, yes, we can preheat up to 600, but we're quite comfortable at 200. As you raise the temperature, there are some issues that we have there, and there are people working to sort of get some stability there, especially when you cross your 500 going above, we tend to have some issues in terms of maintaining the temperature there. So, but there are people working on that currently to sort of come up with solutions for us to see how can we implement high temperature preheating. Prof also mentioned that we also have a smaller version. We call it the Hummingbird, which is exactly the same as the AeroSwift in terms of the parameters. It's also equipped with a 5 kilowatt laser. And this system really, we designed it so that we can do all our process development there. We can do a variety of materials. Obviously, the bigger system, we cannot be playing around with different materials. There's a high risk of contamination, but with the smaller system, it's easy to manage. We can easily switch between different materials from titanium to aluminum and stainless steel. So yeah, SLM solution is already ahead, but we are also still in the race, and we hope that one day we will be able to achieve the goals that we initially set for ourselves. Now, this brings me to the aim and objectives of the study. So what we really wanted to do was to look at the influence of high laser power on visual stresses and porosity, and of course the surface roughness. The objectives here, we manufacture test coupons using high laser powers. We characterize them to measure the surface stresses at the top surface, and also characterize the surface roughness using microcity. We then also did some characterization of porosity. And then lastly, we were trying to actually see if we can correlate build rate with the development of visual stresses. Quick overview of the methodology. So the powder we used is TS64 with a particle size range of between 24 micron to about 51 micron. The system uses the smaller version, which we refer to the Hummingbird. We varied the laser power and the build rate. The build rate is influenced by 3 factors, which is your scanning speed, your hedge spacing, and your layer thickness. And in this instance, I'm only going to be disclosing the build rate. I'm not at liberty to disclose the actual scanning speeds and your hedge spacing. So instead, we revealing the build rates and the laser power. We used XRD, common method to measure your residual stresses on the surface. And yeah, these are just some of the parameters that we used and the constants that we applied when we were doing the measurements. So you'll see that in terms of laser power, we varied the laser power from 2000 and down to 600. Well, these parameters actually stem from another experiment where we started by developing the process to identify a parameter window, which gives us the least porous samples. So we identified these ones as parameters of interest for further investigation. So in terms of the technique that we use XRD, so for those who don't know what XRD is about, so we use X-rays to measure the lattice spacing between your atoms. So we sort of use that as our strain gauge. So each material has got its unique lattice spacing. So with that, after using the Bragg law, we can actually determine the D spacing. And if it's above the constant value, we know that the material is under tensile. If it's below, then we know if the material is under tension. So we use the Hooke's law and the sign method to actually determine the spacing. So I mean the Brecht's law and the sign method, yes, to calculate, to determine the spacing, and from there we can calculate the stresses using the Hooke's law. Micro-CT, similarly, we just apply X-rays, but now these X-rays are not the same ones that we use for X-ray, for residual stress measurements. These ones are able to penetrate through the material. So you rotate the material, on the other side, you have a detector that actually captures the images. And then later you can actually see through the material, see the pores in a 3D space. So these are the two techniques that we used in our studies. We used XRD for measuring the stresses on the surface. We used micro-CT to characterize the porosity in the samples, and then also to measure the surface roughness at the top. So some of the results that we were able to obtain. So here I'm showing you the graphs in terms of the principal stresses. S0, S45, this just indicates the different directions. S0 is actually along it's perpendicular to your scan's direction, and then 45 diagonally, S90 represent along the scan's direction. And then I'm also showing graphs of the porosity measurements and the images obtained from micro-CT. One thing that we know about the residual stresses in LPPF is that it's mainly thermal stress, and therefore the stress at one point is related to its corresponding thermal history. The stresses are high along the scan's direction because the tracks mainly shrink along the scan's direction. This can be seen as S90 in our stress graphs. S90 represents your scan direction. And then another thing that we picked up was sample 1 and sample 3 shows a decreasing trend in residual stresses with decreasing the H spacing. So this can be interpreted as the effect of rescanning. So you can imagine if you reduce your overlap rate between the tracks, you are going to have a lot of remelting, and that will sort of help in terms of reducing your thermal gradients and ultimately reducing your thermal stresses in the part. So you can clearly see this with sample 1 to 3, because that's where we only varied the H spacing, and that's how the other samples we are varying the scanning speed. Sample 7 had the highest porosity when we did the measurements. Even see on the images, the worst one. And then of course, when we looked at the surface roughness as well, it was also the highest. There's some kind of a correlation there. So the rougher the surface of your layer, you must expect to have some more porosity in your surface. But of course, in additive manufacturing, there are other factors at play that can influence porosity. For example, your layer recoating consistency. If it's not consistent, you can sort of have areas which are not covered. You'll have a bed that is not uniform, and then this is going to influence the melting mechanism, and then you are likely to end up having some random porosity in your samples, which is one of the contributing factors in terms of random porosity in SLM parts. The stresses on the top surface are tensile because shrinkage of the top layers is restricted by the underlying, and this is clearly described by the temperature gradient mechanism. I've tried to explain that previously in my background and motivation. And then here we try to see if we can sort of see any trend in terms of build rate compared to when we look at the residual stresses as a function of the build rate. Not so obvious relationship because of the existence of porosity in our samples. We know if you have high porosity in your samples, it's going to relax the stresses in your part, and then this is going to influence your measurement results. However, when we look at the high power samples, which were produced at 2000 watts, where we varied the H spacing, we can sort of see an increasing trend between the residual stresses and the build rate. Yes, as you increase your build rate, the residual stresses develop. And then this can be interpreted as the effect of the scanning time. So you can imagine if you're increasing your build rate, most likely by increasing your scanning speed or increasing your layer thickness, this is going to sort of give you high thermal gradients because now the interaction time is less. So you're going to end up having high thermal gradients in your molten pool, between the molten pool and the underlying material, and this can actually lead to the development of high residual stresses in your part. So based on that, we draw some preliminary conclusions. We can see that in terms of the actual measurements, low porosity below 1% can be achieved using high laser powers and increased build rates. We can see that with the 2000 kilowatt, 2 kilowatts parameters, we're able to get quite low porosity levels below 1%. Residual stresses on top but tensile and found to be below the yield strength of TI64. Residual stresses decreases with decreasing the hedge spacing and the scanning speed. And then another thing, when we look at the top surface, we can conclude that the top surface of the sample processed at high build rates, it was actually smoother compared to the other samples processed at the lower build rates. And then this really has to do with the increased overlap rate that we are applying. So, and sort of this influence your morphology of the layer and gives you this kind of a smooth surface. But of course, from the micro CT images, we only characterize the top surface, and this does not talk to the vertical surface, which is an important parameter as well. And this has not been part of this presentation. It's been a focus of another study that I've also presented, but I'm not going to be sharing it here. It's still ongoing. I'm still doing some tests on it, where we actually focus on the vertical surface roughness, characterizing it and doing some post-processing, seeing how we can improve it and how this affects your part dimensions or accuracy, and then how it also influences your mechanical properties. But for the focus of this study, this is where we ended. And then the other study that focuses on post-processing and characterization of the vertical surface and the resolution of the part. Because you're obviously using a larger spot size, you can almost expect to have a high roughness, and this is going to influence your part resolution. So I'm going to end my presentation here, Maxim, and hand over to you.
Okay, Washington, thank you for your nice talk. Please ask questions. We have some time. We are not in our timetable, but I'm not in a hurry. That's why please ask questions.
Okay, I can ask. I can ask. Okay, my question is the following, that I understand that we can describe, we can measure porosity, but I look through your article, 37 pages, and here is some citation from this article. Thermal and mechanical post-processing methods can relieve residual stresses, but cannot reverse in stress-induced distortion or cracking. My question is, do we have some perspective to overwhelm this problem? If it is impossible to reduce this problem by internal methods too. Do you understand me?
Yeah, I think I sort of get the question. So you're saying, is it possible to relieve or manage this problem in situ? Building process rather than applying post-processing? Is that the question that you're asking?
I guess he is asking about cracking. Can you make crackless builds or so?
Oh yes. Of course, in our system in the past, we were successful to produce some small components which were crack-free. But one of the methods, like I mentioned initially, is to apply preheating, high temperature preheating of the base plate. This is known to reduce your thermal gradients during the build, and it helps to sort of minimize the distortion in the part. But of course, it's not always efficient depending on the size of the part. The larger the part it gets, your preheating may at some point no longer be effective as you grow the part. And other methods that I've seen other people trying, they sort of do some pre-distorted design. Yeah, they use sim effect to simulate the stresses. If are areas where you're likely to get high distortion, and they do some pre-distortion. So they sort of pre-distort it in anticipation that it's going to distort. And when it does distort, it distorts to the actual design of the component. But yes, I think preheating is the most efficient method to go by. And the processing parameters may not necessarily work all the time, depending on the material that you are manufacturing and the size of the component that you are using. But yes, I think it's possible to produce crack-free components if you are applying the right scanning strategies, or you are putting some support in the right areas, and then your simulation is actually closer to accuracy. You can be able to identify problematic areas. Then I think, yes, it's possible.
Okay, thank you.
Are there any questions? More? Please.
Yes, can I have one?
Please.
Yeah, thank you for your presentation.
One of your Alexander, you've got echo.
Okay. Yes.
Can you hear me?
Yes, we can hear you twice or 10 times.
Sorry. Alexander, I think we are connected with two devices. Maybe you may want to switch one off. Are you connected with two devices?
Maybe Yura will turn off his voice.
I have two devices, but I have only one microphone, so it's strange. And
are you close? Are you closer to someone who's in the same meeting?
Maybe. And now the problem is
no, something is wrong. Something is still wrong.
Yes, there's interference.
Can tell us something with it turned off.
1, 2, 3. Can you hear me?
Okay, okay. Ask your question in this way.
Your best.
Yes, we will try our best.
So one of your results was about what should we do to reduce the porosity? We should use more power. If I get you right. Is it right?
Well, not necessarily. If you increase the power, you cannot just increase the power alone as a parameter. So you need to compensate it by something, either by adjusting the scanning speed or the layer thickness, so that you spot size as well. Because if you just keep the spot size fixed and increase your laser power, you're going to increase the intensity in the laser processing zone, and you're going to have a lot of sputter. This is going to create problems. So it needs to be balanced. So your power density balanced with the
exactly. But I see the formulation of your result. We can go back and in this formulation, I thought it said the increased power is we need. Yes, exactly. I want to hear this because as well I think we cannot raise the power as on the method. Okay. Because it's eventually make more porosity.
Yes, agree with you.
Okay. He wrote that we should increase building speed, building rate. And I have also one question, because it was something that surprised me, that you told that you can reduce thermal stress by increase hatch spacing. Have you adopted some other parameters or so? Because you see, you've got more thermal input if you have low hatch spacing. That's why it's something like which surprised me. Could you please comment on that?
Okay. You're saying with regard to the hedge spacing. Yes, how I interpret it. So if you reduce the hedge spacing, the distance between your adjacent tracks, you are likely to have remelting of the previous track. So you're going to get it. So remelting sort of is some kind of a heat treatment. It's going to give you some tempering in the structure. So if you keep on applying remelting of the track, eventually you're going to relieve the stresses in your part because you're sort of minimizing the temperature gradient between the neighboring tracks.
Yeah, I see. I got it. Okay. So, and also, have you investigated your porosity-free samples, and have you compared the thermal stress? So, have you excluded the porosity from your investigation of thermal stress?
No, actually, I did. Okay, I'm not sure if I understand your question, but we did characterize porosity in these samples as well.
You see, they both
measured both the self-test
each other. That's why.
Yes, that's why in some of the results, especially when you look at sample 7, you can actually see even in that group which were produced at 600, the stresses were sort of a bit lower compared to the other ones. So we say when you have stresses in your part, you expect it to relieve the stresses. But I'm not sure if I'm answering your question. Maybe you may want to clarify again your question so that I understand.
Never mind. We won't spend our time. I think we should go further. And only one small question is: have you cut your samples after these investigations? So, have you looked to the real porosity?
Yes, we have done that, but this is not part of this results because microcity. Well, microcity, when you compare to image analysis by optical microscope, microcity is more accurate because you're looking at the entire sample. So when you have this data, there's really no need to go and cut it and look at the porosity. But we have done it in any case to characterize the microstructure.
Sorry, I'm sorry. Okay. Thank you. I can talk to you later, maybe if I have questions. Sure. So I suggest to proceed with another presentation. So are you ready, Ifi?
Yes, I'll be using Prof. Caesar's laptop. I'm in Prof. Caesar's.
Please start your presentation.
Hi, can you all hear me?
Yes.
Okay. No, my apologies for the earlier difficulties. So my name is Mathoho. From South Africa, based at the CSIR. I joined the CSIR about almost 4 years ago. So this only means that I've started learning about this process since I joined the CSIR. So today I'll be having a short presentation about the modification of H950 condition for 17.4 PS stainless steel produced through direct energy deposition. And so I'll just quickly jump into my introduction. So we as the department or the laser enabled manufacturing found ourselves in a collaboration with a company known as ILIT, which manufactures this aircraft, which you can see here. So what happens is at the bottom there's an engine mount bracket. So these brackets are actually 3 of them. They are the ones which are responsible for holding the engine of this aircraft. So now this company was interested, so they asked us to do a feasibility study to see if we can manufacture this bracket through DED, because currently what they do is they procure a casted a block, and then they machine it to make this component. And this component, as I said, is made out of 17.4 pH stainless steel, and they choose this type of material because it's suitable for the application. It has got excellent mechanical properties and outstanding corrosion resistant. So now the problem came when we did process development. We did find our optimum process parameters for the lens. We were able to produce something which was dense. And then the problem came when we apply the post-processing, which is the H950 condition. So that bracket, it's in an H950 condition. So an H950 condition is an aging condition for 17.4 pH stainless steel, which you subject your material to 510 degrees for 4 hours, followed by air cooling. So when we applied this type of condition to the 17.4 pH, which was produced through the lens or DED platform, we found that the mechanical properties were way off. As you can see here, we requested a sample from that side so that we can do our own characterization, and it's named as received. And at the bottom there are mechanical properties for the lens produced. So you can see they are way off compared to the as received. So these results are the one which prompted this study. So now we had to do a modification of H950 condition for the 17.4 pH, which is produced through DED. So this brings me to the aim, which this study aimed at modifying the H950 condition for the 17.4 pH stainless steel produced through DED. And then this was achieved by firstly optimizing the heat treatment processes, which is the modification of H950 condition, and through the characterization of the microstructure and the mechanical properties of both the lens produced and the as received samples or specimens. So for us to build the samples, as I said before, we did firstly optimize the parameters for the lens, and we were able to come up with this set of parameters. We had, I think, 36, but we were able to come up with this lens process parameters, which was 300 watts and a scanning speed of 10.7, powder feed rate of 4.7 grams per minute, and then the H overlap was 75%. Then for the heat treatment parameters, because as we all know that something which is produced through DED tend to form texture or anisotropy. So we needed to do solution treatment or homogenization treatment. So we did homogenization treatment for 2 hours and then followed by air cooling. So for aging, we varied our temperature from 500 to 400 degrees Celsius, and we kept our time constant. The reason is we did preliminary studies before and we're using hardness as an indication. And we found that this material seemed to be more sensitive to temperature at that time. So that's why we decided now, okay, since the H950 condition requires you to age at 510 degrees, let's move from 500 downward. And then that's what we did. And so for our results, just to show you that we were able to produce something which was dense, we took our specimen for micro CT scan, and then we were able to find that the porosity was about 0.09. And my guess is that this was just a foreign particle. As you can see, this pore is not really randomly distributed. So we were satisfied with that. And then we did the characterization from the sample we received from that company. And as you can see, as expected, because 17.4 is a martensitic stainless steel, the matrix is martensite. And we also found using EDS, with the help of EDS, that there are niobium precipitate forming. The reason being that since this is a stainless steel, and with stainless steel you need chrome, this niobium is added as a sacrificial element to prevent the formation of niobium chromium carbides, because if they form, they reduce the corrosion resistance. So you are bound to have this niobium precipitate, and they also help in terms of increasing the strength. So furthermore, with the help of EBSD, we did measure the grain size, which was 73 microns. And we also did XRD, which confirmed the faces present. We had return austenite, as expected, and then we also had martensite. So coming to the modification of the H950 condition, as I mentioned before, that we started at 500 going down. So if you can see there at the top, when we aged our 17.4 at 500 degrees Celsius, the hardness was still high comparing it to the S received. You can see there's a difference of about 100 HV. And also with the strength, if you can see the graph on the bottom left, the strength as well was still high, way too high. It was about 1.3 compared to 1.4. And mostly the elongation as well was way too low. It was about 6% as compared to 50. So we had to move from 500 to 450. And from there as well, we couldn't find our optimum until we went to 400, which gave us a better mechanical properties which are similar to that. And what is more intriguing about this is that we were able to achieve these mechanical properties at lower temperature and also at a very minimum time. So remember, I said H950 condition, you age at 510, so it's about 100 degrees less, and also about 3.5 hours less, because we aged at for 30 minutes, and then we were able to achieve the more or less similar mechanical properties. Another interesting thing that we did find was that if you can see, these are XRD results. If you look at the XRD patterns for D and C. So for C is for the optimum aging condition, or the modified H950 condition. You can see that we managed to get rid of the retention of austenite, or we manage to suppress the retention of austenite. Whereas for the sample of S received, the austenite is there. So now this is important, especially for engineering application, for a component that which undergoes mechanical loading. Remember, return austenite is a metastable phase which tend to transform into brittle martensite upon loading. So it's good that the one we produce doesn't have return austenite, but it can still have elongation. So we further looked at the grain sizes. You can see, even in terms of grain sizes, for the S received, it was 73 microns. And then for the optimum one, it was about 28, which is, there's a huge difference. And you know, in terms of metallurgical perspective, grain growth is not really recommended. So I think this brings me to my conclusion. So the current study concluded that the modified H950 condition can perform better than the S received and standard specification, because the S received microstructure had return austenite, which is considered as a metastable phase that can transform into brittle failure upon mechanical loading. And then the other part is that the mechanical properties that were obtained seem to be better or almost the same as that one of the S received. Thank you. This brings me to my end of my presentation.
Thank you, Ipvi, for your short but very interesting presentation, as you controlled the microstructure of your build part, which is very essential to me. Any questions? Then I will ask a question, and maybe some other people will. Okay. I'm very interested in your presentation, as I'm doing the same, almost the same in modeling. That's why it's very interesting for me. So could you please return to the previous slide? Yes, this with the grain size. And what was the grain size for aged at 500 degrees? Have you measured that?
No, we didn't measure that. It was due to budget, because I had to just focus on the one which gave us the conditions that we're looking for. So I didn't measure that one.
Okay, and have you got any correlation between the hardness and the grain size?
Yeah, there is. You can see for the S received, it was 400, and for the at aged condition, it was higher. So there is a correlation. There is a trend between those two. Mm-hmm. Yeah.
I can't see the grain size here, but
no.
I mean the grain size vs hardness. It is.
Oh no, I didn't compare the two. But I'm just saying, if we compare now, you can see there's a trend. You can see the hardness, the S received had a very high grain. Had a very high grain size, and the hardness was 400. And as for the aged one, it was 28. And the hardness was a little bit higher compared to that one.
And a small question more, that have you tried to control your microstructure by as build samples? So is it possible to use as build samples without that condition after that?
Sorry, can you repeat that, Maxim?
I'm asking that have you tried to control the microstructure of as-built part without any condition after that, without edging?
To control it?
To control the microstructure of the as-built part. Have you tried to do that?
No.
And can that part be used without any treatment after that?
No, we couldn't, because let me go back. Yeah, because I did a summary. So as received, in an as-built condition, the strength is low as well as the elongation. The elongation is very low. I think it was around 6, somewhere there, if I'm not mistaken. But it was low, so we can't use it in an as-built condition. No. Yeah.
Okay. Okay, thank you. So maybe some other questions. I guess
seems like there are no questions.
Yes, I guess we have no questions. Maybe we are very tired now.
No, there's someone.
No, it's Washington. I think I get the where Maxim is coming from, actually. So basically, he wants to know if it's possible to obtain a microstructure that will yield the good properties without applying heat treatment by just controlling maybe your processing parameters.
Yes.
Maybe that's something that can be investigated, or you think, in your opinion?
Okay. No, I get what you mean. Yeah. Then that will be a study on itself, because that will mean you will have to find optimum parameters just for the optimum microstructure that you want to have, which will be a bit tricky, but it's worth investigating.
So
maybe we can Maxim, maybe we can do that. You can help with simulation, and yeah.
This is exactly what we have done in our project, in our joint project with Washington and Prof. Pityana. That's why let me start my presentation now.
Okay.
It's almost 2 hours, but okay, we've got one more from me. Could you please stop your presentation, demonstration, and I will start mine. So, oh, I'm sorry. So, as I said, I'm lucky to have a joint project with South Africa, and here are the results on what we've done in this project. So, aiming to make a robust numerical model for microstructure control in laser additive manufacturing. So here is the outline. There would be short introduction. I will tell about model calibration, verification, and validation. After that, I will talk about the single track microstructure control and also a layer microstructure control. And after that, some preliminary results on narrowing contour optimization and the conclusions. So everybody know the what additive manufacturing is, and exactly laser metal deposition. So it is used for complex part fabrication using layers, layer by layer technique. So, and it is very high value. It makes high value products. That's why numerical modeling can be applied to this technology. And here is my view of how simulations should work for this technology. In engineer in laser center can send a part design to the computer center, where the optimal building strategy will be developed numerically and could be returned to the laser center engineer. But unfortunately, we are not here now. And even in nowadays, simulations are used only in the investigation, and also I show how this could work not in the future but now. So the same engineer can use some web interface to make a task for simulation, for checking some processing parameters, which could be taken by computer center, and the processing map could be developed numerically and returned to the engineer in laser center. But unfortunately, even in this way, it is not working now. But what we are doing is to come near to such schemes. So you definitely need a high performance computing for models which can be reliable and which can predict the processing parameters optimal, or some building strategy. We've got such computer in Shatura. We use open form framework for our for making programs, for making models. It is open source computational fluid dynamic software. We developed the numerical model. I've discussed the model in details in many audiences, and I won't stop here on it, as we are having something like more manufacturing workshop. That's why if there are some questions on the model, please ask, but I won't stop on that. So we developed the model to calculate the microstructure. So it is a coupled model which calculate hydrodynamics, thermal conduction, and the rapid crystallization. And we managed to after that, we managed to calculate the average grain size, which is gained at some processing conditions. And we use the model for our investigation of laser metal deposition. But what I call the robust model is first of all a reliable model that starts from the verification of every part of that model, and that was done by us in our case, in the case of our model, and we start from the hydrodynamic part. We used some analytical solutions to compare, and we show that our model are very good and can reduce the spurious currents that spoil the performance of the hydrodynamic models. That's why we can improve the performance of our model also. After that, some few words about the microstructure model calibration. You see, it is known that the model is needed to be calibrated on the data different to the data which is validated. And we've done that in this way. There are numerous kinetic parameters in the model, but most of them are could be understood, and only one is the surface energy, which could be used for calibration. We've done that using experimental data, and we blocked. So we blocked these kinetic parameters, and so we didn't change them for our different data. After that, we validated the results of the model. It showed rather good comparison with the experimental data for the microparameters of the track and for the microparameters of the track and for the macro parameters of the track, excluding the penetration depth, which could not be well resolved in our model, but we are not aiming to investigate penetration depth in our future calculation. That's why it's not a great problem. So I would like to talk about the processing parameters influence. It is rather well known how they influence the single track parameters. They are rather straightforward. A lot of papers have been published to date on these relations, on these correlations. So, so everybody know that scanning speed increase results in average size in decrease and the width decrease. So we see the same in our model as twice increase of scanning speed results in a little bit less smaller track and twice decrease of the grain size in it. But in our investigation, we are aiming to the track geometry preservation, while having a possibility for the microstructure control. That's why we use the laser power, which has opposite influence on average size and width. That's how we can adopt laser power to have tracks with similar geometry and different microstructure. So at last we managed to get such similar tracks which are very similar in the modeling but not so similar in the experiments, and also we've got not twice decrease in micro average size, but only 20% decrease, but still we can control the microstructure of single tracks and have their width and height the same. This is done for, as you know, the additive manufacturing goes through layers. That's why we can have these single tracks same, and we cannot optimize the scanning strategy, so we can do it only once. And when we need to change the layer microstructure, we don't need to optimize parameters of the scanning strategy. So we have a rather good correlation with the experiment. With the experiments, we published this paper already recently, and we are now working on the single layer microstructure, where we also managed to show the microstructure control while preserving the layer geometry. So we've got an increased average size on low speed and a decreased on a high speed. This paper is almost ready, but it's not finished. We have some minor problems with that, but still we've got these in layers. And also I'd like to present some results on the narrowing on a thin wall, so a contour on a thin wall which narrows. So you can see here that if we go for this contour, the defect occur without any optimization due to the increase of energy density per unit length. And we show that even a decrease in laser power cannot improve this defect. Only small improvement is here due to that the additional powder is still caught by the narrowing, even if we preserve the melt pool parameters. After that, we show that we can get mostly defectless narrowing by using a focused powder beam. You can see by white circle is a powder jet, which is higher than laser beam, but if we focus it to the same dimensions as laser beam, we can have almost defectless narrowing. But still we've got these defects which can be harmful. And we show that only the focused powder jet and the focused laser beam without increase in energy density per unit length can make such defectless narrowings. So here are my conclusions. We developed a robust numerical model for microstructure investigation in laser additive manufacturing applications. We showed a method for changing average crystalline size while closely preserving the growth parameters. We also show that the microstructure could be controlled in multi-track laser cladding. And this allows us to build the parts with a defined quality without any optimization of layer geometry and scanning strategy. And at last, we show that laser power reduction and powder jet focus improve narrowing contour, and laser cladding without energy density per unit length change enable defect-free narrowing contours. That is all. Thanks. So, any questions?
I would like to ask you about the perspective, about your plan on in the future. For example, you describe crystallization, but what about austenite, martensite, chemical reaction? Because of in practice they use a different kind of alloys with many components of inside. Do we have some kind of perspective here for description?
Yes, I understand what you ask. I think that these complex chemical reactions are the question of the building design, which I think could be excluded from the optimization before starting the building by using some well-known powder or so. I have not thought about modeling something more complex, because I think it's I have a rather complex model. So what I am thinking about perspectives is that we can go to the first of all to the building of multi-layered structures, and also to the functional properties of the laser cladded tracks or layers or builds. So something like hardness and so on. Have I answered your question?
Okay, thank you.
Please ask me something, because I can't ask myself. Okay, never mind. I think we are very tired now. We've got almost 2 hours working. I think we can finish our workshop. I would like to thank you, everybody, for being here, for making this discussion. I would like to thank the presenters for the interesting presentations. And yes, I would like to continue our work despite the fact that our project is now finished, almost finished. And I think we can make more good results, more good publications.
Publication activity. Okay, wish you.
I guess somebody has disappeared. Prof. Pityana, can you hear me?
CSIR.
Yes, he disappeared. I think
Yes.
we're all only together.
Yes,
Okay.
I think he might have been disconnected. But on our behalf, I would like to say thank you for this opportunity, for this platform to actually share some of the work that we do at the CSIR, and also for collaborating with us with this project. It's been quite an interesting project from the onset. I've had my skepticism on onset, but having been part of it, I think we have done some interesting work, and we really look forward to more positive collaborations in future. And thank you once again for this wonderful opportunity.
Thank you too. Best regards from Russia.
Same.
Prof. Pityana,
So much.
Prof. Pityana, are you back?
Yeah, it seems as if I don't know what happened, but I'm back now. Thank you. I missed what you called and said at the end.
So we're now finishing. I think we had a good collaboration. I would like to thank you for this work and for these presentations. So
Thank you very much. Thank you for working with us. I hope in some other format we'll continue. Whether we pay for each institution pays for itself, we'll see. But it'll be nice to continue in some other format. We appreciate it.
okay,
Yeah.
let me stop this. Goodbye, guys.
Goodbye. Thank you very much for coming, participating to the leadership colleagues. Thank you so much for your support.
Goodbye.
Bye-bye.
Bye.